All right, we have questions on the homework?
Yeah, I was hard.
Okay, let's know which ones do we need to do? Number,
Number 1E. I was gonna say.
Yeah, letter E.
well, maybe the answer is not correct, maybe.
I just didn't know how to.
Double integral
Wasn't I good?
4 minus y squared dx dy with omega the region bounded by y squared equal 2x. This is the one you asked me yesterday, Acho.
Oh, yeah.
Okay, let's draw the region here. To make it easier, you might want to equate these two, so you get 2x equals 8 minus 2x. 4x is equal to 8x equals 2. So when x equals 2, y equals plus or minus 2, right? So this one is a parabola opening to the right. This is a parabola opening to the left. 8 minus 3, 2, 3, 4, 5, 6, 7, 8. So, yeah. So this is the region. So do you want to integrate with respect to x or y first? What are you doing, Joe?
I'm so tired.
Are we integrating with respect to x or y first? Y. Are you sure? I think we're gonna, because x is gonna go from this curve. Remember, you gotta do the constants last, yeah? So x is gonna go from here to here. So which is the one on the left? Okay, if you solve for x in this equation, you're gonna get x equals y squared over 2. And then in this one, if you solve for x, you're gonna get x is equal to 8 minus y squared over 2, correct? So x is gonna go from y squared over 2 to 8 minus y squared over 2. Right? It's gonna go from here to here, right? And then you integrate with respect to y, and then you just go from here to here, -2 to 2. See how the last one has to be the ones with the constants? Because you can't be plugging in variables in the last step. Okay, like I told you yesterday, the hard part is setting up the integral. Now the computing of the integral is the easy part. So what is the no, we did it, right? We're integrating with respect to x first. So what's the antiderivative of this with respect to x? 4 minus y squared times x, right?
Yes.
From y squared over 2 to 8 minus y squared over 2. So plug in the top thingy, and you're gonna get 4 minus y squared times 8 minus y squared over 2 minus, plug in the bottom thingy, and we should have factored out, why didn't we factor out, I'm gonna do it again. Why not factor out the 4 minus y squared? That would have made it a lot simpler. 4 minus y squared times, plug in the top thingy, 8 minus y squared over 2 minus y squared over 2. Now you're going to integrate this with respect to y from -2 to 2, but look at the symmetry you have. Maybe we should have gone 0 to 2 and times it by 2. Okay, whatever. This is it. So what you have to do is you got to multiply this out. So
Hey, you said
yeah, so factor out a half, and then you're going to get 4 minus y squared times 8 minus 2y squared. Why not factor out a 2 then? Okay, so then we got 1/2. Well, if you factor out a 2, it cancels the half. So you get integral from -2 to 2 of 4 minus y squared, yeah? dy. So multiplying that out, you get the integral from -2 to 2 of 16 minus 8y squared plus y to the 4th dy. And then you got 16y minus 8/3 y cubed plus 1/5 y to the 5th from -2 to 2 I think you know what, let's go 0 to 2 and times by 2 because of the symmetry. Oh, but you know what, we gotta make sure this one is symmetric too, because remember, this is a three-dimensional thing coming up like this. Is it symmetric? Is this thing symmetric about the x-axis?
Yes.
Okay, then 0 to 2, and then we just times it by 2. Okay, so plug in the top number, 32 minus 64 thirds plus 32 fifths. Least common denominator, 15. So you got 2 times, what's 32 times 15? Let's just leave it 32 times 15 for now. Minus, what is 64 times 5? 320. Plus, what's 32 times 3? 96. Can we do all that without actually multiplying out the 32 times 15?
No.
Yeah!
Okay.
Because look, this is 32 times 10. So these two things, if you factor out the 32, you can get 15 minus 10, which is 5. And everybody knows 32 times 5 is 160, right? So 160 plus the 96 there is 256 times 2 over 15. That's 512 over 15. Is that the answer?
Yes.
Yeah. Hey, I still got computational skills. Believe me, when you get old, they disappear quickly. So again, the key is to set up the integral. So are we okay with setting up the integrals?
Can you also
Just the setup,
yeah.
or the whole thing?
The whole,
Okay.
Who said the whole thing?
or the set.
Did you even try it?
Yeah.
Joe, your stock is plummeting. Double integral e, gosh, I can't even see that, e to the negative y squared over 2 dx dy with the triangle. So before we figure out which one to integrate with respect to first, we need to figure out, or at least draw omega. Y equal x plus 2, y equal 1, and the y-axis. So this is the omega region. This is like, and then it's coming up like this, yeah? This one is definitely not symmetric. So, what do you want to do first? You want to integrate with respect to x first from here to here, and then y will go from 0 to 1? Or do you want to integrate with respect to y, go from here to here, and then x will go from 0 to 2?
Which
Let's go with y first.
Okay, so we're gonna go from here, this one, to that one.
Yes.
So we're gonna integrate with respect to y first, and y goes from here to here. So that's x over 2 to 1, correct? And then we integrate with respect to x, so that's gonna go from doom to doom, 0 to 2, right? Because isn't that 2? That's why it's kind of important to draw omega so you can see what, and it doesn't really matter which one you do. So we're gonna integrate with respect to y first, but there's a problem. Do you see the problem? What's the antiderivative of this?
We don't know.
That's right, we don't know, we can't find it. So that means we need to do it the other way. So this one is a no can do. Oh, then no wonder I picked this problem. So let's go with respect to x first. So if I do it with respect to x first, so y equals x over 2, you gotta solve for x. So this is x equals 2y. So that means we're gonna go from here to here. So what is that? From here to here. What's the equation of this? I'll give you a hint. It's x equals 0.
0 to 2.
0 to 2y. And then we're going to integrate with respect to y last, so it's going to go from here to here. That's 0 to 1. Oh, this is clever, this problem. I like, this is a test level question right there. So first of all, we're going to integrate this with respect to x. So what is that? Except I forgot the over 2, yeah? Integrate that with respect to x. Come on, that's easy.
X.
E to the negative y squared over 2 times x, right? Because you're treating that as a constant. From 0 to 2y, let's factor out the constant. So you get e to the negative y squared over 2 times 2y minus 0. So that's simply, let's write it over here. 2y e to the negative y squared over 2. And then now we got to integrate that from 0 to 1 with respect to y. And see, now that integral we can do, right? What technique am I using? Cho, you're not shaking the camera, are you?
Oh no.
Stay away from that desk!
Okay.
Cho, what technique am I going to use to
Oh,
integrate this?
substitution.
Okay, so use substitution. U equals negative 2y. Ah, I should have asked you what is du then? Wait, I copied something wrong. It's not
What?
2y squared, it's just y squared. That would be dumb to put 2y squared over 2 anyway, right? Yes, it would be. So if u equals negative y squared over 2, what is du? How?
2 is y.
No.
It's negative y dy.
Okay. So substituting it in here, what is this? That's e to the u. Y dy is negative du, and then what? This 2 gets thrown outside. And then what are my new limits of integration? Remember when you do a substitution, the limits of integration change, right? So if I plug in 0 for y there, you get 0. If I plug in 1 for y there, you get negative half. The antiderivative of e to the u is e to the u from 0 to negative half. Factor out the constant, and so you get e to the negative half minus 1. What the heck, let's distribute. No, let's just leave the answer like that. Is that the answer? Yup. Oh, I like that problem. So it kind of forces you to do it one way. Okay, anything else? I don't know, I'm looking at the problems for the first time now. Okay, we'll move on. Today we're going to do polar. So before we do that though, let's review what we did last year in BC. Hope you guys remember something. How come everybody's so tired like right now? Even all my other classes, BC,
A lot of
AB.
apps were due.
Oh yeah, yesterday there's a lot of applications due. But I didn't do anything, I'm just tired.
Lose money.
We didn't make it.
Regular admission?
Yeah, you don't have
You
regular
don't.
admission.
UP.
You
Okay, last year when do you guys remember when we integrated for like polar, like for example, what if it said find in fact, well, let's do a problem. R equal 1 minus sine theta. If I were to draw this graph, what is it going to be? 1.
just get some.
This is good review.
Wait, which quarter was this from?
This is third quarter.
The cardio.
Cardioid, exactly right. And then the fastest way to graph the cardioid or any of the limosons is plot the quadrantal angles. So if you plug in 0, you get 1. You plug in pi over 2, you get 0. If you plug in pi, you get 1. And you plug in 3 pi over 2, you get 2. There's Johnny. You guys ever watch The Shining? The
Is
scary
that the
movie?
one where like,
Yeah, he goes, here's Johnny.
the one where his face sticks or something?
Yeah.
Oh, that sounds right.
So you remember how did we compute the area of polar curves last year? You think of it as a sector of infinitesimal width, right? Look, I drew it in for you. A sector of infinitesimal width. So, how do you find the area of a sector? Going back to pre-cal and trigonometry? Okay, let's pretend we don't know anything.
That's probably.
Oh my goodness. Okay, how do you find the area of a sector?
1/2 R squared.
Okay, too late already. Okay, what's the area of this whole circle?
R squared theta.
No, the whole circle.
Or pi r squared.
Pi r squared. And isn't this sector just some fraction of it?
Yes.
What fraction? Theta over 2 pi, correct? Okay, so the pi's cancel out, and oh, what a surprise, you get 1/2 r squared theta. That's how you find the area of a sector, but this is a sector of infinitesimal width, so this angle there is infinitesimally small. So it's 1/2 r squared d theta. Does that sound familiar from BC last year?
Yes.
Because
Oh, yes, it
plus
is.
polar was on the AP exam, people, or you guys just memorized and purged.
That too.
Oh no, you're supposed to say no.
No.
I just kind of forgot, Mr. Park.
That
And then, so, you just have to plug this thing in for R there, right? And then you're gonna add up all of these sectors from, so you're adding up all of these sectors like this. All the way around. And then you get the whole area, right? So it's 0 to 2 pi. Because remember, theta goes going like that, right?
we can just do half.
You gotta think polar coordinates, not rectangular coordinates anymore. Okay, okay, so does this ring a bell from last year? Okay, now, what about, we have a double integral. So, suppose we have a three-dimensional figure coming up like this, okay? So, can we integrate in polar coordinates? And the answer is yes. So, what we're gonna do, instead of, we're not doing this though, because we're gonna do a double integral. So suppose you have some polar region like this. So what we're gonna do, I guess we can do it like this. So you have a sector of infinitesimal width, but then we're gonna take a tiny piece out of it like that. Just like when we did the double integral in the rectangular coordinate system, in omega, we took a infinitesimally small rectangle like this, dx times dy, right? Okay, but what is it in the polar coordinate system? Let's see if you guys can figure it out.
d theta.
Okay, d theta, that's this angle.
dr.
dr,
Yay.
that's an infinitesimal change in radius, but we're missing something.
The z.
Integral.
No, r.
Oh.
It's r dr d theta. See, so in the rectangular coordinate system, your infinitesimally small square like that is dx times dy. But this infinitesimally small, I guess you can kind of think it as, it's pretty much a square almost. It's r dr d theta. Now, how do you think of that? Because dr is this, the change in r, right? Infinitesimally small. What is r dr? Well, let me ask you this. Not r dr, r d theta. What is r theta? Where did this come from?
The arc.
Arc length is r theta, right? So when you have an arc length over here, that's r theta. But if it's infinitesimally small, it's r d theta. So r d theta is this infinitesimally small piece right there. Dr is that infinitesimally small piece there. When you multiply them together, you get the area of the really tiny rectangular-ish thing there. And then what we're going to do is we're going to add them all up. So it's going like this. So again, you have to decide, are you going to integrate with respect to r first, and then d theta, or d theta, then dr? Now normally, you're going to integrate with respect to dr first, because usually d theta is going to just be constants, but you just never know. So, why don't we do the same, as an example, the same problem we did yesterday. Remember the paraboloid that lies above the xy plane? Remember how long it took us?
Very well.
Yeah, so can I erase this now? Too bad I am. So, okay, I kind of forget, what was the equation we did yesterday? 4 minus x squared plus y squared, right? That's the paraboloid that lies above the xy plane like that. Okay, but this time we're going to do it using polar coordinates. So again, what's that infinitesimally small piece right there?
R dr d theta.
R dr d theta. But then That's just the base, and then you gotta multiply it by this infinitesimally thin height. And what's the height?
Z.
Oh, what am I doing? Y. This is Z. That's that, Z, which is 4 minus x squared plus y squared, right? And then you just add them all up. Then what you gotta do is figure out the limits. Now, the thing is, when you're integrating with respect to r and d theta, what are you gonna do with this x squared plus y squared? You gotta remember your polar coordinates conversions, right? Well, what is x squared plus y squared equal to? R squared. So anytime you have x squared plus y squared, in your expression, that's kind of like a hint, you should use polar coordinates. Okay, so let's look at omega. If we project this onto the xy plane like that, omega is this circle of radius 2 like that, right? So which one do you want to, so this one's actually going to be really easy. So since it's a circle, r is going to go from 0 to what?
2 pi.
No, r. R is the distance from the
0 to
origin.
R.
0 to 2. Because isn't this r equal to, in the polar coordinate system, a circle of radius 2?
Yeah.
Because r represents how far you are from the origin, right? So r just goes from 0 to 2, and theta is going to go from 0 to 2 pi. So both of them are constants. So this integral is going to be super easy. Do you guys remember what the answer was yesterday? I forget. 4 pi? Something pi, yeah? Who took notes?
It was just pi.
Oh, it's pi. Okay, let's see if we get the same answer then. So if I integrate with respect to r, you got to multiply this out first. So that's going to be 4r minus r cubed.
Oh wait, it was 8 pi,
Yeah, I
sorry.
see.
Okay,
That's
well
what I
let's
was
see.
thinking.
Well, let's see if we get the same answer. If not, we're in trouble. Antiderivative of this, 2r squared minus 1/4 r to the 4th from 0 to 2. Plug in the top number. 8 minus 4 minus 0, so you get 4. Now you got to integrate that with respect to theta from 0 to 2 pi. So that's 4 theta from 0 to 2 pi. Plug in the top number, 8 pi minus 0. Bagoosh! Ho ho! Yesterday it took the whole part, and now look, it just takes a few lines. And then later on, we're going to also have cylindrical and spherical coordinates too. So when you see a problem, you got to ask yourself, okay, should I do this in the rectangular coordinate system, the cylindrical coordinate system, or the spherical coordinate system? Because I'm not going to tell you. You got to know. Okay, there was one more thing I was going to tell you. Oh, here. You know when you do a double integral of r dr d theta? What happens when you integrate with respect to r first? Like, what's the antiderivative of that? Gosh, I can't even write it. R dr d theta. 1/2 r squared, and then you do it with respect to theta. But see, that just reduces down to the same integral we learned last year in BC, right?
Wow.
Remember 1/2 r squared theta? We just did it 5 minutes ago.
Yeah.
Yeah, so it's pretty much the same thing. It's just a different way of thinking about it.
Wait, so the basic equation used for that one was like z times.
Yeah, because r dr d theta is like this tiny piece, yeah? This
Yeah.
tiny rectangle. But this is like a 3-dimensional surface coming up like this, like that. So, how do you find the volume of this infinitesimally thin, I can't say strip, prism? Yeah. Wouldn't it be the area of the base times the height? The area of the base is this, the r dr d theta. And the height is the z coordinate, right? Okay, so looking at tonight's homework, well, let's see if there's any challenging problems. Yeah, there's only 5 problems to do. Oh, look, I gave you the formula too. Find the area inside the cardioid but outside the circle. Okay, so some of them are, the first 2 are just 2-dimensional problems, and then 3, 4, and 5 are 3-dimensional problems.
Wait, there's no.
So when you do problems 1 and 2, even though they're 2-dimensional, don't do it the way we did in BC last year. Do it the new way we learned. Why, you want me to do one of them?
There's no MVC 3.
There's no what?
There's no worksheet 3. It just goes to 4.
Really, honestly?
Do you have that? It just went from 2 to 4.
Okay,
Oh.
okay, it doesn't matter. I
I
thought
have
you,
MVC too.
you have
You
3?
do?
Yes.
Look at it.
Oh yeah, I got that too.
What?
So that's a triple integral. How come you're missing it?
I don't know what it's down. Whatever.
Okay, and do you want me to do 1 or 2 for you?
Yes.
So you only have 4 problems to do.
Oh, yeah.
Okay, I'll do number 1 and that's it. You guys, Cho, your stock is plummeting. Time, Cho, your stock is just plummeting.
What? It's okay.
Oh my
Goodness. Find the area of the region that lies inside the cardioid, r equal 1. By the way, this is number 1, plus cosine theta. I'll tell you what, let's just set up the integral then.
God. Yeah.
But outside the circle, r equal 1.
I have no idea what
Okay, what is the graph of r equal 1 plus cosine theta?
it's a card. Is it a card?
It's a cardioid. So plot the quadrantal angles. So it's going to be 2, 1, 0, and 1. So inside the cardioid, right? But outside the circle, r equal 1. So like this. So this oh gosh, that's terrible, that chalk. This chalk is not good to shade in things. Okay, that's the region we want. Now we're gonna do this using a double integral now. Okay, so you gotta kind of think of it like this. Here's a tiny little piece out of it, rectangular piece. What's the area of that tiny piece?
R dr theta.
Okay, r dr d theta. Now, if I'm going to integrate with respect to r first, then r is going to go from here to there, right? So where is here and there?
2. Wait, 1 to 1 plus
From
cosine.
2,
Wait, 2.
because from here, oh, what am I saying? From 1 to there, and where's there?
1 plus cosine theta.
1 plus cosine theta. Everybody see that? And d theta, theta is going to go from, I guess, here to there. Or shall we just go there to there and times it by 2?
Times it by 2.
Okay, so 0 to where is right there?
Pi over 2.
Yeah, that's a duh, yeah. 0 to pi over 2 and times it by 2. Or you could have just gone negative pi over 2 and go like that. See how you gotta think polar you gotta think polarly. And then can you guys compute that, or should we just all do it? No, you know what? You guys need to practice, because I can do this. You guys gotta practice. Oh no, we can just do it together then. What the heck? Just do it together. Okay, so 2 integral pi over, okay, so do the, why even write that down yet? What is the antiderivative of r?
R squared over 2.
Okay, 1/2 r squared from 1 to 1 plus cosine theta. Factor out the constant, 1/2, and you're going to have 1 plus cosine theta quantity squared minus 1. Gosh, look, I can't even write things. See what happens when you get old? Then you got to multiply that out. 1 plus 2 cosine theta plus cosine squared theta minus 1. The 1's cancel out. Now you got to integrate this with respect to theta from 0 to pi over 2, and then we're going to times it by 2. Which of course that 1/2 cancels the 2. So all we have is this. Now again, what's the only way to integrate cosine squared?
1/2 plus cosine 2 theta over 2.
1/2. You want to just go 1/2 plus 1/2 cosine 2 theta, or you want to? Yeah, you can't factor that. Let's just leave it like that. So the antiderivative of this thing here, Jason, When
Oh, sine, or 2 sine theta plus 1 plus cosine theta, which,
what about this one?
oh, well, yeah, like 1, yeah.
One
half
half.
theta,
Plus
You look at this guy.
plus 1/2 sine theta.
from 0 to pi over 2. Plug in the top number, Cho.
2 plus pi over 4 plus pi over 4 plus 1, 4 plus 1/2.
Plug in the bottom number, Park. 0 plus 0 plus 0. So your final answer going to be, shall we make a least common denominator? Or shall we just go 5/2 plus pi over 4?
Yeah.
You just leave it like that. What's the answer on the bottom? Wait, the answer on the bottom is not that.
Wait, when you do cosine squared something, isn't it 1/2 cosine?
Oh, it's 1/2 plus 1/2 cosine 2 theta.
Yeah, that's
How
confusing.
come nobody caught that?
'Cause I thought you.
Only Ha caught it. So 1/2, so this changes, yeah? This changes to what?
Sine
Just
2
sine 2 theta.
No, wait.
Oh, 1/4, 1/4.
Oh, wait, no.
Oh my goodness, look how terrible that is. So this one changes to a 0. Now that's a 2. Okay, now we get the correct answer. Woo! All right. Okay, so now you only get 4 problems for homework.
Really?
Okay, let's make it count. So tomorrow we start, do I see you tomorrow? Yeah. Tomorrow we start triple integrals.